let's move on, I think. People are getting tired, so maybe this will exhilarate you. Okay, so in this lecture, how about let's take a 5-minute break, and then we're gonna stop at noon. So 5-minute break, and then we're gonna go for another hour and a half. So this is it's completely different, I think. So we talked about, if you remember, what was the first day? NSD and fMRI, and we talked about how you like approach fMRI data conceptually, including functional connectivity, which was kind of its own thing. Now we're just going to talk about really statistics, but I'll try to link it to subtraction and then VPA where applicable. But there's no fMRI in this, really. And it's a bit crazy because we have one and a half hours to get through. It depends on your expertise level. So I guess some of you who don't have a lot of statistical background might get lost, but I'll try to make it interesting for everyone. Okay, so basically, I guess in the spirit of this workshop, this is like modern advanced statistical non-parametric stuff, not like boring statistics. So that's the goal here. And you can think of these as, it's not specific to fMRI. It's not really specific to any of this analysis approaches. These are like general good things to know, hopefully. And yeah, as I mentioned, a kind of theme here is they're non-parametric. So let me give a quick definition of that. So parametric is like making assumptions of Gaussianity, whereas non-parametric is like things that don't really make those strong assumptions. And the problem with assumptions is they can be wrong. And so these non-parametric methods have a cost. Basically, they cost computer time, and they cost programming time if you're programming them yourself. So if you know how they work and you're good at programming and you have fast computers, then you're good to go. Okay, so and some of this material is taken from this source, which you can look at, and you know the slides are available, so don't bother to write this down. The first slide here is actually a precursor to all of this. Don't do fancy analyses until you've looked at your data, or at least this is me on my soapbox. So I'm going to give you a little example of that. And this example, oh, and I should mention, like, it's not, be prepared to spend a lot of time just looking at data. It's not easy. I mean, it might involve a lot of programming, a lot of looking at figures. I mean, that's kind of the flavor of the examples yesterday, coding those little movies. I mean, yeah, if you find a little software thing that does it for you, great. But it took some time to develop that little code thing. And it costs a lot of loading time, and you know, you have to know how to do it, and you might have to tweak it. So I'm not saying it's easy, and you have to know how to develop good visualizations, but it can actually yield a lot of fruit. Okay, so here's my little example of that. I'm taking this from one of my papers. This was that thing I wanted to show you. But I'll gloss over the cogneuro part of this. I'll just tell you the figures. So here I'm just looking at data in one area of interest, VWFA. And the y-axis is just percent bold. It's from a GLM. There was an experiment. I'm just going to show you the different stimulus conditions. And this is just a manipulation of contrast. And you know, just by ordering the stimulus right and like using line elements and showing error bars, you can kind of get a lot of information about what's going on in this one brain area. So we manipulated contrast of different types of stimuli, and then you know, kind of lay it out nicely and make it visible. This is mean and standard error across subjects. And then we did that under you know, different task states. The subject here was fixating and doing this little dot task. And then due to experimental design, we kept everything constant and used the same stimuli, but asked the subjects to do other tasks. And so by plotting all of these responses under, you know, done under different task conditions in a single graph, you know, and kind of ordering things nicely, you can already start to see patterns, especially here, that are of interest. But actually, that's not the interesting thing. The interesting thing is going to this plot. So looking at this, I mean, yeah, blue is higher than green, it's higher than red. Maybe there's some, maybe it is especially higher here, but you know, what does this mean about what the brain is doing, or representation? So let's just plot the data differently. right? We're not analyzing data, we're just plotting. So the x-axis here is the VWFA response that we just are looking at here. It's just a completely different visualization. The y-axis here is the FFA response. So a different brain area. It's actually right next door. And we just, average the beta weights within that ROI to the exact same stimuli, look at its data. And now we're going to represent, these responses as dots. This is like state space. Your axes are like neurons or voxels or ROIs. And so each dot is a different stimulus. So each point here is now re-represented as a dot. And we're going to put error bars on the dot because it's good to know what the trial noise is. And the color now, yet another tool at our disposal, we can see color. Hopefully, is anyone colorblind? Okay, you're at advantage. So I'm using color to represent generally which stimulus it was. Like if all of these dots were black, like you would have no idea. Like VWFA responds to what type of stimuli and FFA responds. But now we can use color just to kind of group. I mean, we can't use that many colors because it's hard to. Anyway, we're using blue for generally the face-like stimuli, and yet orange for the word-like stimuli, and gray for things that don't conform to either of those. So we're using color to visualize a different aspect of this. And then we can plot other elements here, like this line. This is a decision boundary that separates these general classes of stimuli. But that's not even the interesting part yet. So I can replot this plot for the 3 different sets of data. So red, green, blue corresponds to this, that, and that. In fact, you can make a movie if you want. Actually, I did make a movie. It's kind of cool, but I can just show you it in a static sense. So it's exact same subjects, exact same stimuli, but all we're doing is changing the task, supposedly, that the subjects were doing, right? And so I was interested, what really is this difference? Yeah, is it just like higher response, or is there something deeper we can say about the nature of how the brain is responding differently under these different states, right? So just by visualizing it in a specific manner, you already start to see something happen. Furthermore, we can visualize like this, like use an arrow, essentially use lines and angles to help visualize the trajectory, in a sense, of the representation, right? So we're just going to plot an arrow starting at the fixation, which is red, and going to say what happens during the third task. So I'm just going to plot an arrow. So now every stimulus is an arrow. So now you're actually representing 2 data points with 1 figure element, an arrow, the tail and the head. So that has some structure. And in fact, we can plot some cartoons of other ways it could have been. So just by looking, you can almost analyze your data. So this specific visualization is, it's kind of interesting, but really the general point is this was the first thing I did before I actually analyzed the data further quantitatively. And then I saw this and I immediately thought, there's a result here. And then, fast forward 9 months and then do all the work and then you're done. Okay. Oh, sorry. I should say, okay, I'll talk some cogneuro. So this stimulus-directed task thing, you might call it attention, behaves like a scaling, right? These vectors come from the origin and push out versus, say, an additive effect or something like that. Okay, that's enough cogneuro. Let's talk about statistics. So first topic is, I want to keep this like fundamentals of these concepts. So regression and classification are the fundamentals, and they collectively fall under supervised learning. So that's like a machine learning term. There's supervised learning, and there's unsupervised learning. We're not going to talk about unsupervised learning unless we get done, and then I can have a whole lecture on that. But supervised learning, let's just start bare bones. You have some input variables. You can call them regressors, call them predictors, and you have an output variable, or you can call that data. And you're trying to learn the mapping between those variables and the output. And you call that a model. And so this is really simple. And this covers both regression and classification. So when the data happens to be continuous, it's regression. When the data happens to be classification, which typically numerically you code as 0 or 1 or something like that, it's just classification, right? And that's it. So like this one framework covers all sorts of things, right? When you do GLM and fMRI, what are you doing? Well, X are your little experimental regressors, you know, the href stuff and the drift terms, whatever. And then your Y is the time series from a voxel. MVPA, so that's the case where your X's are actually now the brain data. So your voxel activity patterns, your vectors, you know, and you're trying to predict the output, which is your stimulus labeling. Was it A or B? And encoding models, I mean, it's basically like GLM, but you know, we think about it a little differently. X are like the different stimulus features that you think are related to the response that you're observing in a voxel. Right, so this is kind of the abstract view, and this is how it relates to all the concepts you've already heard about, right? Okay, so let's just talk about regression first. This is me on my soapbox, and the depth at which you understand regression is a variable, and I would say you want to understand it as deeply as possible, then you reach nirvana. Because it really comes up all the time, and many things are just special cases of regression. Okay, so in one sentence, what is it? It's a weighted sum of regressors. On the previous slide, we call them predictors. I mean, they all kind of mean the same thing. It's using a weighted sum of things to fit or match another thing. That's the output, right? So weighted sum. So you have weights. These are just scalar constants. And so you weight a bunch of things and you sum them all together. And that's it. That's all regression is, and it is very powerful. So let's delve a little bit deeper. We need to introduce a few very basic concepts. And so this is really getting at what does it mean to match the data or fit the data. Typically this means squared error. So sum of the squares of the residuals is squared error. And so just mathematically, you have n data points, D is a data point, M is your model fit. So how close is your model to the data? Subtract that and square it. And then you sum all of those residuals. That's all, right? So this is the definition of what it means to fit data well. Of course, you could change the metric, and it's possible, but this is the standard one that works out in terms of math very well, right? So little example, simplest case of regression is a scatter plot, X versus Y. These are data points, and we want to use X to fit Y. Okay, so this is one possible fit, and this is a horrible fit, but I just want to plot it. So this is saying, you take X, you weight it by 1/4, right? This is a weight. And let's say there's an implicit regressor here, which is a constant term. But the weight on that constant term is -1/4, right? So this is a 2-weight regression model. That's what it looks like. It doesn't fit the data that well. These are the residuals. It's just the data point minus the model squared sum. So that's not a good fit. And then we can do the same thing with the same data set. Here's the same data set, and then that is the optimal fit. In other words, this weight and that weight optimally matches the data. It has the lowest squared error. Statistics 101. Okay. Even this clicker is dying. I'm going through so many batteries. Okay, so that's kind of the one-dimensional case in a sense. 1x predicting 1y. To scale up, we have to use additional conceptual machinery. So we need to use matrices. And we've seen this, but you're going to see it again. So this is our data set, just 5 data points. One thing predicting another. I'm going to lay out the data y as a vector. So we hit, 5 is in there, and 3, and whatever. So we just lay out the data to be modeled as a vector. We have our predictor, x, it's just the x coordinate. So I'm just laying it out as column vectors. And there is an implicit column of 1s. It's the bias term, the constant term, whatever you want to call it. And we're just trying to do a weighted sum of these two things to fit the y, right? Think of like the fMRI GLM regressors here and the time series over there. It's the same thing. Okay, we're going to call the one the output, call these the inputs, certain matrix dimensions. Matrix multiplication is what achieves that. So hopefully you know how to multiply matrices. It's just W1 times the first column, W2 times the second column, and sum them together. Okay, so matrix multiplication is the core concept of regression. It's a weighted sum of these when you set it up like this. Okay, great. So we have weights. And all we're doing is figuring out what the weights are. Like, what are the optimal weights that minimize the residual, that minimize the squared error? Okay, so just think about this more abstractly. That's the data that we're trying to model. These are our weight parameters, or the parameters of our model. That's our model. Our model includes both the parameters and the things that we're using to model the data. And that's it. So let's just call that y, call that x, call that w, and we're just trying to get the w. We're estimating this w. We know y, we know x, just tell me what the w's are. And that's it. And then of course you can set up with these residuals. To get actual equality, your model may not actually fit the data, so there's this kind of slop term to make everything equal. Okay. Oh, sorry. So the motivation was, now that we've extracted away, I can make x have 1,000 columns, and that's 1,000 dimensional. We can't visualize that anymore, right? So that's the power of setting things up as matrices. Okay. One last way to think about regression. This may or may not fly with you, but I like it. We can kind of represent 3D on a 2D screen like this. And the idea here is now the data are now represented by a dot. So this is a low dimensional problem, I know, but bear with me for a minute. So let's say we have 3 data points that we're trying to model with some regressors. 3, 4, 5 is just, go 3 out, go 4 up, and then go 5 in. So the data can be thought of as a dot. And then your regressors now can be thought as vectors. So here I'm plotting 1, 1, 2. So it's like 1, 1, 2. And I just draw a vector from the origin. And then we might have another regressor, x2, which is just 4, 1, 0, 1. So 4, 0, and then 1, right? And we just want to do weighted sums. So how do you weight and sum vectors? You like crank them up and then add the vector addition. And that's all regression is. So there's a subspace now. So these regressors can get weighted and summed arbitrarily. You can weight regressor 1, 0, and regressor 2 a lot, and you'll end up here, and you can weight them in different combinations, and you basically span out this space. In this case, it's a plane. The subspace is a plane. So the question is, what are the magical weights we need? We need certain weights to achieve this fit. So weight this one by 2, weight this one by half, or whatever, or wait, oh, I was close. 1.5 and 1. So you scale this up, scale this guy 1.5, scale that guy by 1, and then add them, and then you're out here. And that's nice because that is the closest you can get to the data. This is orthogonal, it's perpendicular. That's all regression is. And you can see where this is going because you can expand X with as many vectors as you can. You can have vector this way, and this way, and now your subspace is a 3D space. It's a 3D space. We don't have much more words beyond that. But you can have like 100 regressors in your model, right? You do that all the time in GLM. So you have 100 vectors competing to try to explain the variance in the data. And they're little arrows pointing every which way. And some of the arrows are very correlated. Correlated regressors is just vectors pointed almost in the same direction. Okay. And then just as a comparison case, this is a valid fit in a sense. There are certain weights that get you here, but they don't actually fit the data that closely. So there's an optimal point in the subspace to get maximally close to the data. And that, if you're doing least squares fitting or minimizing squared error, that's the standard regression solution. I see a combination of facial expressions. It's very amusing. Okay, brief breakout. I don't want to make these too long because we have a lot to go through. I'll just take volunteers instead of calling up. Yeah, there you go.
We're talking about here why you use 3 dimensions to demonstrate the 2-linear regression for this example.
Yeah, 3 dimensions. It's to make it non-trivial. So, and this actually relates to Boss' point. Any other? I'll answer that in a second. Any other comments? Okay. So I didn't include a constant term here, which is typical. I should say you don't have to include a constant term, but it's very common. And so I used 3 because we can see at least 3 dimensions, kind of. And one important point is this plane is governed by where the vectors live. You can't just like move the plane up and down willy-nilly. The plane is a function of these regressors, and I said these are the regressors. Like that was fixed. And that's why this plane can't actually go through that point. And that's kind of the whole point. Like you can't optimally fit every data set and fit all the variants. This is the residual. And this plane can get close, but it doesn't actually intersect that point. If I included a constant term 1, 1, 1 for x2, it's the same deal. x2 would just be a vector pointed towards 1, 1, 1, which is like out here. So now you have this vector and that vector, and they span a plane. And then you're going to try to fit the data, and you won't get 100% fit. It'll get close, and where the closest point is the standard regression solution. And this generalizes, right? You can make 100 data points, and then you have to visualize 100-dimensional space. But the geometry and math intuition still work out.
Not that the people will ever do that, but if you make sure you have an equal amount of regressor to the dimensionality of the data points, technically it can affect to some
Yeah, those are a good point. I should mention that. So let's say we tacked on a third regressor, a constant term 1, 1, 1, a vector that's here. Now these three vectors span the entire three-dimensional space, and so there is a solution that's exactly the data, and you explain 100% of the variance. So in this case, I kept the number of parameters or predictors one less than the number of data points. Hence, we generally expect not to be able to get all the variance. Good? Okay, moving on. So that was regression. Let's turn to classification. Ironically, classification is a lot harder. So for linear classifiers, so think MVPA, standard fMRI stuff, the setup is we're going to use a weighted sum of predictors, same as regression, but followed by some sort of threshold. So threshold means like you like cross the threshold of the doorway and you're like go from A to B, like it just jumps. So a number rises and or at some point you cross a line and then you're on a different side of things. So we're going to use that weighted sum plus a threshold, and then we're trying to fit the data. In this case, like the binary outcome, A or B, or on or off, or whatever it was. The nonlinear case is different, and it's less typical for various reasons. I don't want to get into it too much. But nonlinear basically is a catch-all. Anything that doesn't conform to weighted sum is a nonlinear classifier. So things like squaring or exponentiation or whatever, those are all nonlinear operations. Okay, some examples. Actually, this is just nomenclature. This is just another, or notation rather. Just focus on this part. This is a weighted sum, right? I from 1 to the number of data points. Let's call this the weight. So you have n different weights, a different weight for every predictor. So x sub I is the predictors. So this is just another way to write down a weighted sum. Okay, anyway, so what classification is saying is, yeah, we're going to do the weighted sum. We're going to apply weights to our predictors, great. And we get a number, a constant. And then we're just going to ask, is it less than some magical threshold? If it's less, let's just say the output is 0. If it's greater or equal to, let's just say it's 1. That's all. So classification is just one more layer on top of the regression equation. Okay, so that's the setup. This is really slow. I think it's my computer. Okay, I have some like little figures just to kind of hopefully clarify things, but it might confuse you. Okay, here's our one-dimensional case. We have one predictor trying to predict the data. Data's in red. This is what basically what we saw earlier. This is the one-dimensional case for regression. Easy peasy. Again, there actually are two predictors because we typically include a constant term. Okay, let's talk about classification. So again, we have one thing, one feature, one predictor, x, and the data now is like rounded to, well, it looks weird because it's either 0 or 1. So I'm just plotting the data in red. So these are observed data points. Apparently the outcome was 0 when this predictor was down here, and it's 1 when this predictor was here, 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 here. So you see the red dots, and they're not perfectly separable. You can see like, even when x was 1.2, sometimes Some measurements were like 0, but there were some measurements like 1. Okay, but we can try to fit the data. We can try to get as close to accurately classifying it to be 0, 1, and that is this point. So at 2, we decide, well, if my predictor was less than 2, that's our prediction. If our predictor was greater or equal to 2, that's our prediction. So it's a little step function. And it more or less goes through most of the data. So that's just saying your percent correct is going to be pretty good. And remember, this is a weighted sum. It's x times 1 plus the constant term times 0. Which is, this is what we just saw on the previous slide. Okay, let's go a little more complicated. 2 dimensions, so 2 predictors, which is again a lie. There's actually an implicit constant term, probably. So it's actually 3 predictors. But okay, so we have x1. This is one feature we're using. Think of it as like a voxel. x2 is the second voxel. And we have data points plotted to the circles. And now the color of the circle is the data. So again, we're using visualization. This is very common. Color can represent something. And you can kind of see the colors get brighter towards the upper right. So we have 2 voxels trying to predict something continuous. Sorry. This is regression. So let's think of these as, these are like GLM predictors. We have 2 GLM predictors, and the color is now like time series. And so they have explanatory power. We see that, yeah, as these predictors get higher, so maybe when the trial was on, the response tends to be high. Okay, so we're going to use regression to fit the data. And now you see behind this shaded thing, this is the plane that we have fitted. So we've already done the regression. We've determined the weights to be 2 and 1. So x1, which is the x-axis, got a higher weight than x2, which got only a weight of 1. And you can kind of see the plane is actually more horizontal than vertical. So given this regression fit, given this setting of weights, it implies a fit. The fit is a plane, and we're visualizing that plane using this grayscale. We're actually using the exact same color map that was used for the data. This was on purpose. And finally, we have contours of that plane. So the contours trace out values along the plane that are equal, isocontours. Okay, so you can just visualize what's happening. I have dots in 3 dimensions, but I can't do that on the screen. And we're trying to push a plane through these dots. And so some dots are above the plane, some dots are below. But on the whole, it's tracking pretty well, right? So some dots are smack on. This dot is exactly the same gray as the surrounding plane. That means the plane went through that dot. But sometimes it gets it wrong. So the data says, oh, it's dark, which means low. But the planar value was a little brighter. Anyway, but you can imagine a plane going through a cloud of dots. That's regression and pretty easy. So now I can orient my plane however I like to try to fit this scatter plot. This is the hard case, the classification. So again, the setup's the same. Right? We have the same old weighted sum, 2 and 1. We have 2 predictors. And let's just say the threshold is at 6. So if you actually plot what this looks like, it turns out to be a line that separates 0 from 1. So, sorry, back up a second. The data points are dots. Some of them are deemed 0, some are deemed 1. So now we can think of these as like MVPA. This is one voxel, this is the other voxel, and these are our trials, and each trial is either A or B. And so I'm trying to use these 2 voxels to classify the stimulus that was on the screen. And lo and behold, it's quite separable. I can see the black dots over here, the white dots over here. There's some overlap, but it's not that bad. And I can imagine there's a plane, remember a weighted sum, and after I take that plane and threshold it, and basically say beyond this point, you're 1, below this point, you're 0, you can now visually represent that just as a line. So over here, you're 0, you're over here, you're 1, which is exactly what this says. And you can kind of see that's pretty good. The white dots live largely on this side, the black dots live on the bottom. All right, so what's happening is classification is just this funny discretized version. In 1 dimension it looks like that, in 2 dimension looks like that, and then you have to imagine what 3 dimension looks like. And then you get terms like hyperplane, which is just like things beyond these simple low dimensional cases. Do people like my pretty pictures? Okay, I guess I think visually, so. All right, so and then I'll just briefly mention, there are many classifiers, I'm sure you've heard these, and they're all very similar. So here, let me just plot all of them just so you see a bird's eye view. The data set's not the same across these 5 examples, but they're all doing this, they're trying to do the same thing. They're just trying to plop down this line. And in all cases, the line basically separates black from white. But importantly, you will get different lines depending on what classifier you throw at it. It's like, and the same happens in regression. In the regression world, there are different types of regression fits we can try, and you will get different results. But in classification, it's especially so. So logistic regression, let me try to give you the brief version of these, because I want to get through it. So this will go fast. But in all cases, we have 2 variables trying to predict a binary outcome. Logistic regression says orient a weighted sum, and you get a continuous value, and then pass that through a squashing function. So it's a logistic function. It basically starts at 0, gradually goes up to 1, and then saturates. And you can see that through these contours. You can see the plane, but the plane doesn't like go on forever like the previous plot. It actually is 0 here, is 1 here, and in between it nicely transitions. And logistic regression says, well, let's just put the decision boundary at the 0.5 point, like the mid. And it actually has a probabilistic interpretation. The 0 to 1 range is interpreted as a probability. So it's saying out here, the probability is like 0.01 that you are white, a white dot. And then over here, it's like a probability of 0.3 that you're a white dot. And then here, it's equal probability. Anyway, so that's logistic regression. LDA, very common. Basically, you modeled the distribution of each class as a Gaussian. And that's being shown by these contours. You can imagine this is a nice smooth Gaussian with iso contours as shown. And then given your assumption that that's a good description of the distribution of points, you can then say what is the ideal decision boundary to draw given that assumption, or given that fit rather. SVM, completely different mindset, kind of from machine learning, but basically you're plopping down a line to maximize the margin, which is the distance to the closest points, and you're essentially ignoring all the other data points. Of course, that there's details like what if you can't actually separate them, then there's a slack term and all this stuff. But nearest prototype classification, this is like Haxby 2001. You take all your trials of faces, take all your trials of houses, you just compute the mean across all those trials, and then you get just one point, which is actually an activity pattern. In this case, a 2-voxel activity pattern, but it can be whatever. So it's just the mean of the cloud. It's the center of these clouds. And then your decision boundary is essentially just the midpoint. Well, it's a boundary that's perpendicular to the vector that joins these centroids. So it basically ignores all the noise variability. It just says, I just care about the mean. Let's just keep it simple. And then lastly, this is actually in a case of nonlinear classification. So this is just, okay, let's have a brain activity interpretation. X1 is a voxel, X2 is a voxel. These are training data, so I observe, oh, it was actually white when the brain activity was here and black. But the classification rule is, let's say I have a new brain activity measurement and it lives here, like something I didn't observe in my training data set. It says, I predict the stimulus label was white because I am closest to this point in the training data set. Okay, and then you just do that ad nauseum. So at some point you're like exactly halfway between this being the nearest and that being the nearest. And so that's the boundary. But notice that thing is jaggedy, it's not a line. So it's immediately a weird nonlinear classifier. Okay. So the commonalities are vast. So in both of these seemingly different things, we kind of do the same thing. So we have to choose the model. So this is like, what predictors do you put in your GLM? Or, you know, what, yeah, maybe I'll just leave it like that. And then you also have to fit. So in regression, it turns out to be a matrix inversion. In classification, it kind of depends on the method. SVM is a completely different fitting procedure. Details aside, I mean, in all cases, you have to fit the weights. Find the weights that satisfy whatever criterion that you're set with, great. And then in all cases, you probably want to know how good the model is. So that's like variance explained, or it's like successful classification, percent correct. So accuracy, how well is it actually working? And then in all cases, you probably should care about reliability. So this is like error bars on your beta weights. Like, do you get completely a different result next time you try it on a new data set, or is it fairly stable? So it's like searchlight. Well, you do a searchlight once and you do it on 2 halves of your data. Do you get a similar looking pattern of results or not? So it's like stability of your model results. Okay, so, and I'll just allude to, and we're going to get there, cross-validation is kind of like this thing, and bootstrapping is kind of like this thing. We're going to get there. Okay, short breakout on those topics thus far. Questions or things that weren't super clear? Otherwise, we'll keep going. I mean, yeah. I mean, sometimes you just have to stare at it, but.
You can elaborate on the cross-validation and bootstrapping.
It's coming. Okay. Yeah, this wasn't a break. What happened? So, oops, let me keep going. Oh, we saw this. All right, so next quasi-section of the talk is resampling methods, because it's really an umbrella term for things that are completely different, but they all are like the same thing, right? Mechanically, they're the same thing. And this goes out to kind of the theme of like, these are like computationally intensive and maybe more modern ways of doing statistics. And yeah, and nowadays we have good computers, so we can do it. So this covers 3 things we're going to look at in the next 3 sections: randomization / permutation, bootstrapping, and cross-validation. So first things first. Remember NHST quiz question, what does that stand for? Null hypothesis significance testing. So if you want to do that, then you might want to use randomization methods. Oh, another term might be like shuffling. Like randomization, permute, shuffle, all the same thing. So in one sentence, what is it? Oh, 2 sentences, sorry. You're going to randomize or equivalently permute some data set according to some null hypothesis. The null being the thing that's kind of boring. Like, we'll see an example in a second. And then after you do that, you're going to calculate a p-value based on how unlikely your actual data set was relative to that randomized simulations that you did. That's the whole thing in a nutshell. So this is nice because mechanically it's easy. Like, it's just a few lines of code. You don't have to think too hard. Again, it's a non-parametric thing. Like, there were no assumptions in what I said, really, other than making sure you have a reasonable null hypothesis. So that's nice. And then lastly, there's this property of the simulated data that you did, the randomization, is very well matched to the actual data. So like, you don't want to be stuck in a case where you like, oh, my result is significant because I like simulated some fake data that had nothing to do with my actual data set, and look. But this is like, you use the exact same numbers that you have on your computer, and so it's very, very well matched to the actual statistics of what your statistics in the sense of like mean and standard deviation. It's very well matched to your empirical data set. So these are all very nice features. So in reality, what are some examples? Well, let's say we're doing a GLM and we have some stimulus labels, like 10 stimuli, and you're going to code those stimuli in your design matrix, and you might want to permute them because you want to know like which voxels in my data set actually show some different response to the 10 stimuli. And so if you do nothing and just fit your data, and then you'll get 10 beta weights, and you look at them, they're all going to be different because noise happens, shit happens. And they're going to be different, and then you stare at it and you're like, I don't know. Of course, you can go the route of try to estimate the error bars and that type of stuff, which is fine. But alternatively, or complementary, you can use permutation to kind of assess, well, under the null, let's say a voxel really had no difference in its response to any of the 10. Like, it really either didn't respond at all, it's at 0, and any differences are completely the measurement noise, or maybe it responds exactly the same to all of your experimental conditions. Like it's like a light detector. Oh, there was something, there was something. Anyway, so that's the null. So under that null, it should be fine and equivalent to shuffle the stimulus labels. Like if A is literally equal to B and C and D, just relabel all the stimuli. So you do that, and you can reanalyze your data set according to that new randomized description. And then you will get a result. And then you can do that 100 times. And then you can compare. You have to come up with some metric of like standard deviation across the 10 numbers or something like that. So you have to summarize things into a number. And you get 100 of those numbers, or 1,000, or however many you want, and you start getting a distribution. And then on basis of that, you can get a p-value. So we'll see a figure of that in a second. But conceptually, that's the setup. Another example, so think of a scatter plot. You measure, my favorite example, height and weight of people. So people are independent. You sample a person, you measure their height, you measure their weight, then you start filling in the scatter plot. It's going to be correlated, I bet. So you want to establish, well, is this like, let's say you only sample 10 people, and it's like a weak correlation, like 0.3. You want to establish some p-value on that. Like, was this just some random sampling error? So you can use permutation or randomization to assess that. So you essentially take one of the variables, doesn't actually matter because it's equivalent, but basically you take, let's say this is height, this is weight, just take the height numbers and shuffle them, because the null is there is no relationship. So it should be completely equivalent to reassociate this height with this weight and so on. So you just shuffle, compute your Pearson's correlation, and do that many, many, many times. And then you'll get like a distribution. It will be centered on 0, because if you are comparing two vector quantities and there's no relationship, on average, the Pearson's correlation will be 0. Anyway, so you get a distribution of randomly attained correlation values, and then you can immediately look at what did you actually observe in your actual data to see how likely it is under the null hypothesis. And we'll see a little figure of that in a second. Okay. But before we do so, we have to revisit Statistics 101. So, standard error of the mean. Hopefully, I mean, I could call on people and be like, explain this figure. But you should know this, but it's always good to remind yourself. So this is the normal distribution. Mean 0, standard deviation 1. This is the population from which we're sampling, let's say. Okay, so let's sorry, I have to look ahead. Okay, take that back. The setup is we have two samples, and we want to test, are they different? So we're just doing like 2 groups of people, and we measure something from the 2 groups, and we're computing the mean of each group, and we want to know, are they actually statistically different? That's the setup. So here, we're going to simulate that process from a known distribution. So this is the null, because we're going to draw both groups from the same distribution. There is no difference. The underlying population mean is the same for both groups. Okay, so what does that look like pictorially is like this. So our sample, here it looks like there's 2, but it can be any number of subjects that we draw from this population. We have one sample, it's blue, call that group A. The other sample was purple, call that group B. We compute the mean of the samples, and then we subtract them, right? And so we see a difference. Of course, this is a completely incidental difference because we're drawing from the same population, but they will be different for a finite sample, right? So we do that, and we compute the difference, and then we go over here. In this one simulation, so we can draw 10 subjects, compute the means, and compute a difference. That'll be over here, let's say. Okay, and then we can repeat this as many times as we want, right? We have a population that we're simulating. We can simulate draws. So we do this, and we get this. So this is a very smooth looking thing. So if you do this infinity times and do a histogram, it will look like this. And the reason is this was a Gaussian. So this is, again, if you start with a Gaussian and you draw samples from the Gaussian and you compute something like this, the resulting distribution will be also a Gaussian. And that's the point. So now we can look at the actual data set, which I'm not really showing, and look at how unlikely the actual difference in means was relative to this distribution. So I'm going over this because that's the logic behind the actual randomization thing we're going to see in the next slide. Okay, and to get the p-value, you basically quantify unlikeliness in terms of the tails. So if you're way out here, that's extremely unlikely. So you're going to reject this null hypothesis. Okay, so let's see the exact same logic, but with randomization. And kind of the point of randomization is it works really well for non-Gaussian data. So I'm going to show you a case where the data look quite weird. Like, it is what it is. This is what we measured. And these are like 10 subjects in one group, and then 10 subjects in a different group. So the x-axis is the value that we care about, the measurement, and then these are color represents these two samples. So this is the actual data set, and you can kind of guess whether that's significant. I mean, it looks okay, but it's not super clear by eye. And of course, we could plot the mean and standard error and do that type of thing, but these are the raw data points. So let's just use randomization to do a formal null hypothesis statistic significance testing on this. So the mean of each group is this dot. This is actual, I think I actually computed it. So this is the actual mean of the red. This is the actual mean of the blue. And we're gonna start building up stuff over here in a second. So, but now let's do the randomization. So randomization just says, under the null, if there's actually no difference between the two groups, you can essentially treat them interchangeably. And so you just essentially shuffle the labels. So this dot will get a coin flip. Do you belong to red or blue? I don't care. Just stick them into a different group. So here's one of those randomizations. You essentially just shuffle the assignment to the groups. Okay, so this is a quasi new data set. We do the same thing. Here's the mean of the blue, here's the mean of the red. Let's store that away. Okay, now let's do this 1,000 times. So you do that again, you do a random assignment, you get a new answer, great, do it again, you get a new answer. And then you do that again and again and again, and then you get a histogram eventually. Or you get 1,000 results, you do a histogram. So now you kind of see like, oh, under the null, yeah, we could have easily gotten like a -2 or a 0.2. Like there's some spread. Like, so this helps us understand how unlikely, again, this is all under the frequentist framework, but given our actual data, red minus blue was -0.4. Yeah, look, that's actually -0.4. It actually works. Okay, so our actual data set lived out here. So this looks pretty far in the tail. So the p-value is, whoops, is probably less than 0.05. So we're done. Buying questions, or people are confused, or boss is confused. Issues? Yeah.
Like if we have 10 data points, is it okay to like sample 20 data points?
Wait, 10 to 20? Wait, you want to draw a sample the same size as that you actually have.
Yeah, just
Yeah, for sure, because otherwise it's fake. Like, you never collected 1 million subjects. I mean, you could simulate what would happen if you collected 1 million subjects, but that's not an accurate estimate of what you actually have in your data set. So you want to draw a sample size of 10 if you have 10 data points. Question?
I think I'm missing something essential. So I understand conceptually what you've done here, but I don't understand what we've gained from, like what we've learned from actually putting some.
You learned that, dude. That's it.
Okay.
The uncertainty.
Can you say more? So this distribution is clearly not normalized. If you do this parametrically, you would always get symmetric error bars.
Okay.
Yeah, so the results will be potentially different from a more parametric route. And it's like, sometimes you can't, no, I won't go there. Any other issues before I move on?
Well, I mean, there's the question of like uncertainty about what,
In,
what kind of inference do you make from that?
in this case, it's uncertainty on the median, if that's what I wanted to compute on my data.
But I mean, the median is the median of the data, right? So you're
Right.
talking about some other hypothetical experiment
Right.
that you do.
It's hypothetically the population median that I'm trying to.
Right, but it's a population that looks very much like the population that we had at hand.
That's right. So yeah, and this kind of come up before, like if you only have 3 subjects and you really want to know something at the group level, like none of these methods can save you because you're either biased because of convenient sampling, or you just have 3, so it's just completely too small of a sample size to really do much. So that's a deeper problem, I would say.
Well, all I'm saying is that there is a philosophical difference between these methods and parametric tests. I mean, you're absolutely right that we don't make assumptions about the data being awesome, right? But that's a little bit underselling what they're actually doing for you, because most parametric statistical tests are actually robust against non-analytic data, right? So if you're just about that, yeah, you may gain a little bit, like, you know, just about that. Most of these methods are, you're not going to do a type 1 error, right? It might lose some power if the data is not balancing, but it's not going to be an error in the data. So there's more to these than just, you know, oh, the data is not balancing, therefore I'm going to bootstrap.
Okay, the third of the 3, cross-validation. It's also a very simple idea. Actually, I don't know if you agreed bootstrapping was a simple idea. Maybe it's a complex idea, I don't know. Okay, so the underlying idea is performance. I'm gonna use that term instead of, right? I mean, all these terms kind of mean slightly different things, but in regression, it's like squared error or like variance explained, but let's just call that performance. Or in classification, it's like percent correct. Let's just call that performance. Oh God, accuracy. Accuracy is like, oh, I have some neural data, like how good are you at modeling the real data? Anyway, so whatever you want to call it, what that number you get on training data, so in this case, it's the data set you have on your computer. Like you actually measured it, and let's say you were just to model that data and try to fit it. It's always, I hesitate to say always, unless you do something fancy, it's overly optimistic. Like, I can generate random numbers and then generate a random regressor, and I can fit variance in that random data set. I can always fit. I always get like at least 3% variance, 5%. I can always fit the data. But it's overly optimistic in the sense that it won't actually work in general. Like if you have, well, that's the whole point of cross-validation, but, and which we'll get to in a second, and you can think of this as bias. Like the number you get, 3% variance explained, it's like too high. That's, you're fooling yourself. So the simple idea is we're just going to use left out data out of sample in a sense. Or typically, I mean, it depends on how you want to approach it, but typically you just get a set of data and then you post hoc divide it and say like, that's the left out data. And then you have training and testing, right? So the idea is then we're going to use left out data that you don't actually analyze in order to quantify your actual performance level. So in theory, this is unbiased. Like it's going to be noisy. Things are always uncertain because you know your left out sample has only like 10 subjects or 10 trials, whatever. And you will get a number, and you know that number is not truth, but on average it should be unbiased. Like it should not be higher or lower on average than what the true value should be. All right, that's it. And that's a resampling technique because you take the data and like you have to do some random number generation and you just like chop the data in half or whatever. Okay, so as I kind of said, you choose a subset of data to leave out. The data you're left, you train on, or you fit your model on, or you do whatever you want on. And then you go back to the test set, or the left out data, to predict that data set. Or I'm going to use the word predict because really it is a prediction in some sense. You're going to try to classify that left out data, or you're trying to assess how well your model works on the left out data. That's the basic setup. And you know, there's all sorts of different ways you can call this. You can call your training data, you're estimating parameters on your training data, and then you're going to validate your parameters on the left out data. You can also use fit and predict. So fit is very boring. It's like, oh, you're just fitting your data. But predict is like, ooh, we left out some data. Is it actually going to work? You can also, and again, training and testing is, so people use these terms interchangeably. You just have to choose whatever way you want to say it and use it consistently. Okay, one big question is like how to really divide up your data. So I'm just going to mention, just keep it simple, 80-20 is kind of a rule of thumb. Like use 80% of your data to train on, and then leave out about 20% of the data to test on. But I mean, that's just a rule of thumb, and there's trade-offs. So like if you're fitting a lot of parameters and you have a model that needs a lot of data to get trained on, you probably want a lot of training data. So you want to make that big, but if you make the testing set small, you're going to get a really noisy estimate of its performance, right? If you just so happen to pick the sliver of data that really stunk, you might have a great training model, but you'll fool yourself. Oh, it didn't work that well. But so there's a trade-off going on here. And that just implies one split, but you can of course do like n-fold. So n-fold is like divide your data into say 10 parts, train, and we'll see a figure of that in a second. So there are all sorts of ways to approach this. And of course there's a choice of like, do you leave out trials or subjects, and it kind of depends on what you want to do. So these are all kind of open questions. Yeah.
So the rule of thumb is for when you're not doing n-fold, or is it also for?
Oh, that I don't know. My guess is either. 5 is like a magic number, maybe 1/5, but I'm just guessing.
Just doing like MBPA, I've found generally you're better off with more noisier samples. So with doing like leave one out type cross-validation than I am with fewer, more robust samples.
I see.
Using like leave one run out.
Right. Yeah, that could be. And another consideration is computational time. So if you have 30,000 data points, you want to run your analysis 30,000 times, I'm not sure. Okay, so real world examples, obviously MVPA is the obvious one. Another one is completely different, but you can think of it like this. Like let's say we're in neuroimaging world, we are like developing cortical maps of stuff, and you have like thousands of subjects, which we don't have in NSD, but in other data sets you do. You can easily leave out entire subjects and then do like resting state on 999 subjects and like try to predict something about the 1,000th subject. So how you apply this is the world is your oyster. So here's the little schematic just to make it super painfully obvious. Here's some hypothetical data. In this case, we're going to leave one out. So these might be runs or subjects or something. So red means use this to train your model. Gray means test it on that one. And then we just do this 5 different times, or 6. So we train, test, and then reset, train test, reset, train test, and so on. And then one way to kind of aggregate the results is the following. So you could say, let's say this is a whole run of data. So you have a predicted time course, say, of that run. So you can kind of put that here. And then you have a predicted time course for the second run from the second iteration, and you put it there. And then you can just lay your full data set out and just like compare them. So that's leave one run out, I guess, if these were runs. And yeah, I'm not clear whether 80-20 is best. I mean, you could do fivefold, which is basically this, but you divvy up your data into 5 parts. Okay, so that's the procedure. So now let's kind of think about both bootstrapping and cross-validation. So probably it's a little unclear like what the difference is or how they mesh. Is that like you get it or you're unclear? Okay. So I think just repeat this in your head. One's about reliability, one's about accuracy. So okay, let's step through this figure. We have the exact same data set being shown 4 times. And it's one-dimensional, one thing trying to predict another. This is, I guess, regression. It's a continuous output, y. Okay, this is one type of model we can apply, a very simple model. It's a linear model. It's a weighted sum of the x trying to predict the y. There's an implicit constant term, of course. And so I fitted it with the line. And I think I bootstrapped this thing. So what I did was, I took the data points I had, I drew bootstrap samples, I fit each sample, and now I'm summarizing how wiggly those fits were across 1,000 or 100. And I'm showing that as like a little confidence interval. So I'm putting a shaded region around the central, I don't know, 75, 95% or 68%, I forget. But this is some error bar on how stable my line fit was using bootstrapping. I think, yeah, I said I bootstrapped, so I did. Okay. So that's the linear case. And look, the error bar, it's tiny. That's good. So I know, I mean, it's definitely significant, but it's more than significant. Like, it's really tight. Like, I know the estimate here is really good. So we can do the same thing with some other models. So this is, we didn't even talk about this, but this is the same data set, but I'm trying to fit this relationship between x and y using a completely different model. It's basically just adding a squaring term. So you're allowing x squared to be a player in the game. So I can fit that model, I can bootstrap the procedure, here's the results. So you do this again with a completely different model. This is a nonlinear model, and just briefly, it's not linear because this is not a weighted sum of x. This little pesky n made it nonlinear. It's an exponentiation. But it's a model. You can, this is just math, right? You can evaluate y as a function of a times x to the 3rd power or whatever. And I can fit that model. And I can bootstrap it, and there are the results. And finally, crazy non-parametric case. So this is a different thing, non-parametric, a different meaning of non-parametric. It's not like statistical distributions. This is non-parametric because one definition is this model grows with your data. Like if you have new data points, the model completely changes. Whereas here, if you have new data points, these fits, the model doesn't increase in its complexity. It's like, it's always just 2 parameters. Whereas here, this is a nearest neighbor regression. It says the fit for a data point is just the y value associated with the nearest data point. In fact, we saw this in the classification world a couple slides ago. But anyway, that model looks like this. And it also has an error bar because we bootstrapped this. And I did the exact same crazy procedure. Okay, so I showed various flavors of models, but the point is bootstrapping. What did bootstrapping do? It showed us the reliability of these model fits. 4 different models, and each of them has a different, well, they're all different, and they have their own reliabilities. And notice, well, they're actually very similar, but this guy actually is the most reliable, it looks like. I mean, there's a little bit of error bar there, but like it basically goes to 0. And this guy's the worst. He wiggles around a lot. So by bootstrapping, we learned something about the reliability of the models we got out of our exercise. What does cross-validation do? Well, if you look at these plots, like in which case does the blue line go through the data points the best? Like, don't worry about the error bar. Just look at the thick blue line. Which one actually? Bottom left. Oh, sorry. Oh, no, you're completely right. No, this wins. But this is the overfit. Oh God, that's the next topic. I'll have to do this in 4 minutes. So yes, if we're talking about fitting data, this guy always wins. Like, it fit all the data, right? And in fact, the blue line does go through all the data points, but it's completely bogus. Like, it's overly optimistic. But anyway, the answer is this guy. This guy is the true best model. In fact, the data were simulated from this model. So if we actually do the cross-validation, you know, we can leave out this data point, fit this little linearized model, and predict it, and then do that n-fold. So I'm not graphically depicting that process, but let's say I did do it, and I did, and then we can measure the model accuracy or the performance, and this is the actual result, I think. This is not, you know, this is real results. So we have, you know, linear, the funny squaring one, and then we have the nice power law, and then we have the nearest neighbor. Nearest neighbor is the worst. The best was the power law model. So this black bar is not actually symbolizing how well the blue line went through the dots, but it's actually the cross-validated version of the blue line. And this is getting at the fact that this non-parametric, very powerful, fit a lot of data thing was actually learning not a good representation of the underlying XY relationship. So bootstrapping, cross-validation are getting at completely different things. The bootstrapping is telling you like how stable is the model you're getting. Notice that the linear model is very stable. Like it's pretty good. Like if you saw this, you'd be like, wow, my analysis results are really stable. But in terms of accuracy in describing why, it's actually not the best. I mean, it's good, but not as good as you can get. So you can be high reliability, but low accuracy. Okay, in 0 minutes, I will move on to the last bit, which is overfitting. What is overfitting? We kind of saw a depiction of that in a second. And I'll just get to the figure, because really you learn by, well, I learned by seeing pictures. This is very traditional. Okay, so we have data, it's noisy. These are actual samples from some underlying model. So the model is cubic, but I get noisy data. Okay, if all I see is red, I try to fit the data. I try to like model the data. I try to get a good relation. So I can use a constant term, and that's what you get. I can use a linear term, that's what you get. I can use a quadratic, I can use a cubic, I can use a quartic, and so on. So I'm just increasing the complexity of my model, throwing more parameters at it. And now I'm tracing out, I'm showing you essentially what cross-validation does you. So if you just focus on the red, as I throw more and more polynomials into the model, red always goes down. So just focus on red. You always decrease your error. And you can see that. It gets closer and closer to the data points every single time. So the error, which is the y-axis, always goes down as I increase parameters. But now let's look at the black line. The black line, I'm calling it population, but just think of it as cross-validation. So if you leave out some data, and at each point evaluate it on that left out data, this is the performance. So it actually is best, least error, right here, which is 3, which is the cubic, which makes sense because I showed you what ground truth was. So overfitting is the fact that this model, number 7, using crazy wiggles, it like wiggled too much. It threw too many parameters at the data. It fit the data too much. Okay, so I'll skip this slide. It's not that important. And then get to the guy that goes with overfitting. So how do you fix that? Like, you had 7 terms in that, you know, 7th order polynomial thing. How do I like make the model better? It was like overfit, and like percent correct was actually really horrible. Well, you regularize. So it's kind of a vague term, but basically means you kind of smooth out the wiggles. You like don't let it fit too much, or you like make the model like less crazy. Like it's too spiky. How do we like push down the spikes and make it nice and regularized in a sense? So specifically, and this is all classic stuff, you can incorporate penalties. So the idea is you don't fit the data. Fitting the data means minimizing the residuals. But we don't want to do that. So instead, we actually minimize the residuals and also try to minimize some other things. So ridge regression is exactly that. So ridge regression is sum of the squares of the weights in the regression model. So remember the weights? You're penalizing big weights. So I think it's very intuitive. You don't want infinity to be one of the weights. You want it to be like 10 or 5. Also lasso, exactly the same idea. You're minimizing the sum of the absolute value of the weights. So it's really just a tiny change on the exponent. So instead of squaring the weights, you just raise them, well, take the absolute value, which is like exponent 1. So this is 2, this is 1 as well. Right? It's also called L2, L1. Anyway, so these are like classic examples of regularization. So the idea is you're still doing regression, you're still trying to model the data, but you're also trying to minimize these other concerns. And as soon as you do that, you can actually start helping your model so you can reduce the overfitting. Okay, then the final question, just skip that point, is how do you know how much to penalize? And the easy and typical solution is you use cross-validation to figure that out. Right? It's exactly the previous figure. I can get there. So how do you know how much regularization? How do you know that this 7th order polynomial was too fitting? Well, I mentioned it on this slide. Like this black curve I told you is essentially cross-validation. So if we leave out some data and evaluate the model and then crank in another term and evaluate the model on left out data, we will eventually see this curve, this black curve. And then finally I know what to use. I should use cubic because it said it was the lowest cross-validated error. I think that's basically it. Let's see. Oh. Yeah, you can just read this offline. Not that critical.